So in this video, I'll be doing practice problems on infinite sequences, mainly finding their limits if they converge. All right. And I took all these problems from past final exams or practice final exams or study guides from an old UCI class that no longer exists. This was Math 2J back then. And this was the class where they taught like half linear algebra, half infinite series. They now merged this class into Math 2B. But of course, these are good practice problems to do because this is probably the same level that you can expect on the Math 2B final if you're taking that class. Or if you're taking some other classes from other university, these could be good practice problems as well. Okay? So, but before starting, these problems should be nothing new, or 95, 96%, really high percentage of them should be nothing new. You've already at this point learned how to find limits, calculate limits. You know the limit laws, you know L'Hopital's rule even. There's only one new thing that you might have learned, in which I'll go over when I get to that problem, or those few problems, okay? Otherwise, these should be not new at all, to be honest. But with that said, if you still struggle with finding limits and L'Hopital's rule and all that, these hopefully will be some good practice problems, okay? So let's begin. So number one, this is from some exam. Each number is probably from a different exam. I don't remember how I picked these or where these problems exactly came from, but majority of them are from different exams that I was able to find. Okay. So different teachers wrote them. So you can see how different teachers word things, and you can see how similar that teachers are expecting, what am I trying to say? That teachers are expecting their students to know the same things, which makes sense. They're at a university. They're held to a certain standard of what they're supposed to teach and what their students to learn. Okay. Enough blurbing. So determine whether this sequence converges or diverges. If it converges, find the limit. Okay, so we have this sequence here. A sub n is square root of n over e to the 2n. The procedure is you just want to take the limit as n goes to infinity. It's always like that. Limit as n goes to infinity of the guy. Let me get my pen. So if we plug in infinity, we get infinity over infinity. So we can use L'Hopital's rule. Remember, you can only use L'Hopital's rule if it's 0 over 0 or infinity over infinity. So we meet that requirement. So we differentiate the top. That's 1 over 2 root n. Differentiate the bottom. You need to chain rule. So it'll be e to 2n times 2. Now we take the limit. As n goes to infinity, the bottom gets bigger and bigger, so we're approaching 0. So this limit exists. The sequence converges, and it converges to 0. Okay? Next, a sub n equals negative 1 to the n power over n factorial. So, I didn't say this beforehand, but if you should try the problems first yourself, and then unpause it to see how I think through it if you struggle through it, and of course to check your answer as well. And I cannot guarantee I got all these correct. I did my best to check my answers, but if I happen to make some calculation error or I did something wrong, please let me know in the comments, okay? So how do we find if this sequence converges or diverges? Well, there's alternating signs, so sometimes it can get tricky. But this is where that new concept comes in. There's a theorem or something like that says if you take the absolute value and take the limit of the absolute valued version, so if we absolute value this guy, the changing sign, that minus 1 to n would go away. So we take the limit as n goes to infinity of 1 over n factorial. That clearly goes to 0. Okay? The theorem says if the limit of the absolute valued version is 0, then this limit with the changing sign is also 0 as well. Okay, so we use that new thing here. This is very important to not be confused with what this theorem says. The theorem says it has to approach 0, the absolute value version. If it doesn't approach 0, let's say it approaches 1. Okay, then would this limit with the changing sign exist? It wouldn't. It would oscillate between 1 and negative 1. 1, negative 1, 1, negative 1, as n keeps incrementing into infinity, all the way to infinity. So clearly the limit doesn't exist there, right? So it only works when it approaches 0. Okay, that's the key concept to understand. And it looks like we have to apply it here, actually. I already gave the answer away by that, but let's look at it. Does this limit exist or not? Does the sequence converge or not? I'm just going to say, does the limit exist as n goes to infinity? Well, again, we look at the absolute valid version. So that changing sign goes away. We take the limit as n goes to infinity of this guy. It's 3. Okay? Now, as I just said, as this guy approaches infinity, well, it's going to oscillate between positive 3 and negative 3. Positive 3, negative 3. Positive 3, negative 3. Clearly, the limit doesn't exist then. Okay? So, again, that theorem only works when it approaches 0, which makes sense, because it'll be like some small positive number, some small negative number, and an even smaller positive number, and an even, technically bigger negative number, meaning bigger as in it's closer to 0. So less negative number, if that makes sense. Okay. Next, does this sequence converge or does it diverge? Does this limit exist as n goes to infinity? Here we can use the squeeze theorem. How did I know that we can use the squeeze theorem? Well, first of all, as n goes to infinity, sine n, does it approach 1 or negative 1? It doesn't exist, actually. But then the bottom, as n goes to infinity, it approaches 0. So it's kind of like indeterminate, but not one of the formal forms. It's not quite clear, because the bottom's approaching 0, but sine n is oscillating. So we can use the squeeze theorem. So sine n is between negative 1 and 1. That's the range of it. And as always, you want to start from here and then make the middle match this. So you just want to divide everywhere by n to the 4th plus 4, which I forgot to write over here, or type over here. And this should be a 4 over here. I don't know what I was typing. Okay? Now we take the limit as n goes to infinity of this guy, that's 0. Limit as n goes to infinity of this guy, that's 0. So by the squeeze theorem, the middle as n goes to infinity also approaches 0. Okay, so this is nothing new, hopefully. That's number 1, okay? Let's get some more practice. Number 2, find the limit of the sequence. A sub n is arctangent of n. So what's the limit as n goes to infinity of arctangent of n? That's pi over 2. You just need to know that. If you remember how the graph looks, it's asymptote, and it approaches pi over 2. How about this one? A sub n, arcsine of 3n over 3n plus 8. Well, as n goes to infinity, what happens? We can use that property of limits for composite functions. So we can first find the limit of the inside, and if it exists, then we can just plug it into the outside. Okay? So that's what I did here. So what's the limit as n goes to infinity of 3n over 3n plus 8? That's just 3 over 3, which is 1. Okay, so what's arcsine of 1? That's pi over 2. Okay. How about this one? N sine of 1 over n. Again, here we can use the squeeze theorem. Actually, do we even need to use the squeeze theorem? We can just use L'Hopital's rule even. Right? So, up to you. So I guess I use L'Hopital's rule here, but you could probably use the squeeze theorem as well. So limit as n goes to infinity of n sine of 1 over n. Well, as n goes to infinity, we get infinity times 0, because 1 over infinity is approaching 0, so sine of 0 is 0, but times infinity, that's indeterminate, but it's not infinity over infinity or 0 over 0, so we got to make it like that in order to use L'Hopital's rule. So instead of multiplying by n, I divide by 1 over n, so now we get 0 over 0, so we can use L'Hopital's rule now. So derivative of sine of 1 over n is cosine 1 over n times derivative of 1 over n. Notice I didn't even bother to find the derivative of 1 over n because if we differentiate the bottom, that's the derivative of 1 over n. Those cancel, so you're left with limit as n goes to infinity, cosine of 1 over n, which is cosine of 0, which is 1. That's the answer. So the sequence approaches 1. Okay, clearly this is written by a different teacher, different notation of the sequence. Determine whether the sequence is convergent or divergent. Again, nothing new. So, again, we just take the limit as n goes to infinity of this. So, does the sequence converge or does it diverge? It converges because we can use properties of limits to first find this limit, which is a constant, so it's negative 5. Okay, and this guy, we take the limit as n goes to infinity. It approaches 0. This is 9 over 10 to the n power. Remember, it's kind of like the geometric series. Well, something positive but less than 1 is a fraction. So you're taking a fraction of a fraction of a fraction. It's getting smaller and smaller. Like imagine you even having something. If you keep having it, like half to a quarter to an eighth, it's getting smaller, right? So as you take more slices or keep chopping it, which is a fraction, then it's approaching 0. So the answer is -5. The sequence is convergent and converges to -5. Next, this one, does this sequence converge or does it diverge? Hopefully this is obvious. This diverges. It oscillates between 5 and 3. Because this is the changing sign, so it'll be 1 or -1. So 4 plus 1 is 5. 4 minus 1 is 3. Okay, so the limit doesn't exist. Doesn't approach anything. How about this one here? Well, it's infinity over minus infinity, sorry. So we can't use L'Hopital's rule directly. We got to use the conjugate if we want to use L'Hopital's rule. So that's what I did here. Multiply the top and the bottom by square root of n cubed plus 2 plus square root of n cubed minus 2. Okay, difference of 2 squares on the top, so we get n cubed plus 2 minus parentheses, n cubed minus 2, be careful of the parentheses, and the bottom I did not touch. So at the top we get 4 if we simplify. Now if we take the limit as n goes to infinity, this approaches 0 clearly. All right, how about this one? Converge, diverge. If it converges, what does it converge to? Clearly, this one diverges. Because this is like a rational function. If you do the degree test, the degree of the top is bigger. So there's no horizontal asymptote. It blows up to infinity, actually. We can do the math out if you really wanted to. I guess I can do it real quick. So it'll be limit. Remember, the technique for these is you want to factor out the biggest degree. So if we factor out n squared on the top, it would be 1 plus 2 over n minus 1 over n squared. Over, we factor out n on the bottom. It would be 1 minus 2 over n. Okay? As n goes to infinity, these would go to 0. That's the whole point. We have 1s left. Now about here. Well, this would cancel. Right? As n goes to infinity, it blows up to infinity. As I expected. Okay? I think there's one more. Yes, there's one more. Okay. So hopefully you're getting the hang of these. Again, this should not be new. It should be review for the most part. Does this limit exist? Does it not? Again, the quickest way to do this is treat it like a rational function. Do the degree test. The biggest degree on the top is 2. Biggest degree on the bottom is 2. They're the same. Take the ratio of the leading coefficients. 3 over 2. How about this one? Which indeterminate form is it? It is infinity over infinity. So we can use L'Hopital's rule. We need a chain rule. Be careful. 2 ln n times 1 over n. That's the top. Derivative of the bottom is 1. So I move this 1 over n as a n on the bottom. So clearly it's still infinity over infinity. So L'Hopital's rule one more time. Derivative of the top is 2 times 1 over n. Derivative of the bottom is just 1. Now as we take n to infinity, we get 0. Okay, how about this one? I think you already peeked at the answer, but that's okay. We can use the squeeze theorem here. How do I know to use the squeeze theorem? Well, as n goes to infinity, what does sine n approaches? It does not exist, right? So, but then again, we're dividing by 2n, so it's like approaching 0 on the bottom. So is it actually approaching 0? We don't know. So that's why we gotta use the squeeze theorem. Again, start from sine n, and then get this to match there. So we have to add n everywhere, and then divide by 2n everywhere. Okay? So now we take the limit as n goes to infinity of this guy. It's 1. Again, degree test, they're the same. Take the ratio of the leading coefficients, so 1 over 2. Over here, take the limit as n goes to infinity, same thing, degree test, same. Take the ratio of the leading coefficients, half. Since they're both half, by squeeze theorem, this guy is also half as n goes to infinity. That's the limit. Okay, what about this one? So whenever there's a changing sign, you could have to think, maybe I can use that theorem. So what's the limit of the absolute value diversion? So limit as n goes to infinity of e to minus n. That's 0. Because e to negative infinity looks like this. It dies down to 0, right? Since this is 0, then by that theorem, this guy is also 0. Okay, how about this one? Again, we can just use that composite function property. So find the limit of the inside first, which is pi over 2. Again, degree test, same, take the ratio of the leading coefficients. So what's sine of pi over 2? 1. Okay, that's this video. Hopefully this is a good practice set for you if you needed it. Otherwise, hopefully you also got an idea of what they can possibly ask, or at least at this university, UCI, common questions they'll ask, common types of questions they'll ask. And it should not be too different no matter what school you're in. Again, most of the time, teachers want you to know the same thing. Professors, instructors, lecturers, whoever's teaching the course wants you, and in charge of the course wants you to know the same things for the future courses, okay? As always, please give this video a like if you found this helpful in any way, and please subscribe as well if you're interested in seeing more videos like this.